Try your microphone, see if you can talk, and I can hear it.
Hello, can you hear me?
Hi, Amir. Yes, I can.
Okay, great.
Thank you.
Hi, everyone. My name is Amir Shehata. I've been working on the Lustre Networking, or LNet for short, for the past 7 years or so. I've worked with the Lustre community to develop several features, one of which is MULT-RAIL. MULT-RAIL is started as a collaboration with SGI, it's HPE now. We phased it out into multiple features which were designed to build on each other. Next slide, please. In this presentation, I'll cover the MULT-RAIL feature set and describe the motivation and advantages it provides LNet. I'll start by giving a quick overview of LNet and why MULT-RAIL represents a shift in how LNet works. Then I'll cover the different phases of the project, starting with the base MULT-RAIL feature. In the next phase, we added health and resiliency. Then in phase 3, we improved the LNet routing infrastructure to use the new MULT-RAIL capabilities. And finally, in the last phase, we add network selection policies, which gives the administrator finer grained control over LNet traffic. With this, let's jump into it. Next slide, please. As I'm sure most of you know, Lustre is a parallel file system used in many HPC environments, and it's gaining traction in other areas such as AI and the cloud. Next slide. Lustre performs its file system operations by exchanging RPC messages between the client nodes, management server nodes, metadata server nodes, object server nodes, and the different target nodes. These RPC messages perform operations like file locking and initiating RDMA operations to get data from the clients to the servers or vice versa. Lustre's RPC protocol is implemented by the portal RPC layer. The RPC protocol is composed of LNet messages. This is where LNet comes in. LNet is in essence a networking abstraction layer. It provides a way to configure virtual networks and assign different interfaces either via their names or IP addresses to these virtual networks. LNet supports different fabrics including IB, Omnipath, Ethernet, and others. This design allows Lustre to be network agnostic. A further abstraction layer yet below the LNet, termed LND or Lustre Networking Driver, implements the fabric-specific protocol. For example, AutoIBLND uses the Verbs kernel API to send LNet messages over IB or Omnipath or Rocky fabrics, while the SOC LND uses the kernel socket APIs to send traffic over Ethernet. There are other LNDs which handle different hardware like Craze or, again, HPE now, Gemini hardware. Again, this design allows LNet itself to only worry about managing LNet messages and not about how these messages are transmitted over the wire. Next slide, please. Before MULT-RAIL, LNet design allowed for only one network device to be configured on each virtual LNet network. This limitation had a couple of main fallouts. It made configuring multiple NICs on the same node difficult, and therefore prevented higher throughput on larger clients or servers. Let's look at an example. Next slide, please. In this example, you can see a large client with multiple interfaces. In order for this client to use all its interfaces, we needed to configure multiple virtual networks, AutoIB0, AutoIB1, etc., and add each of the client's interfaces on one of these networks. However, this had a ripple effect throughout the cluster. All the servers and other clients had to create virtual interfaces which would use their single interface and add these virtual interfaces on the different LNet networks as well. As you can see, the more interfaces you have on a machine, the more complex the configuration will be. There are machines now with more than 8 interfaces available for Lustre. This is where LNet Multi-Rail comes in handy. Next slide, please. First question to ask is why Multi-Rail at the LNet level instead of at the LND level, for example, or why not use Ethernet or IB bonding? To answer that question, we need to look at the requirements we're trying to achieve. We want LNet to have the flexibility of adding multiple homogeneous interfaces to the same network. For example, if a node has 3 IB interfaces, we want to be able to add all of them to the O2IB1 network and use them in active-active setup. By doing so, we will be aggregating the performance of these 3 interfaces, in effect widening the pipe. We also want LNet to handle using multiple network types simultaneously. For example, if we have IB and Ethernet interfaces and the Lustre nodes are configured on both, we want LNet to utilize both network types in active-active setup as well if we so desire. The third requirement is to allow LNet to intelligently select the interface it sends from in such a way as to make efficient use of the hardware it runs on, such as the NUMA configuration or other restrictions that may be imposed on us by the hardware architecture. The fourth requirement is to ensure configuring multiple interfaces as easy as possible. It's now clear that a lower level bonding implementation will not satisfy all the requirements. In fact, the lowest level we can implement multi-rail and satisfy all the requirements would be at LNet. LNet has a view of all the interfaces, the network types, and the hardware configuration available for Lustre to communicate over. Next slide, please. In this diagram, you can see the end goal we're trying to achieve. No longer is it necessary to have multiple LNet networks. All the interfaces on that big client can now be configured on the same LNet network. Of course, this functionality is not restricted to Lustre clients only, but it is generalized to Lustre servers and as we will see, LNet routers as well. Basically, any node that runs LNet. Each LNet node can now utilize all the networks and interfaces available, as well as select the best interface to use. All this can be done with 0 configuration changes on the Lustre side, as well as very little configuration on the LNet side. On the LNet side, only the networks and the interfaces on the networks need to be configured. The node's configuration will automatically be discovered on demand by other peers on the cluster. Next slide, please. I've talked very briefly about configuration discovery in the last slide. This feature, which is part of the base multi-rail phase, implemented a discovery protocol which allows nodes to discover all the interfaces available on the peers they are trying to communicate with. By doing so, the node can utilize the peers' interfaces appropriately. Let's take a quick example to illustrate. If 2 LNet nodes have 2 networks, O2IB and O2IB1, for example, with 2 interfaces on each network, Lustre on the active node, that is the node initiating communication, needs only to know the primary NID, or network identifier, of the peer. The primary NID is the first NID configured on the peer. LNet can then use the primary NID to discover the other NIDs of the peer. It can then spread the LNet traffic load over the NIDs as desired. Once the discovery step is complete, LNet can make intelligent decisions on which local and remote interfaces it can use. Administrators can also configure policies to define extra criteria on how to select the interfaces, as we will see later. Next slide, please. This is what LNet's internal structure now looks like. LNet can have multiple networks configured. Each network can have many network interfaces. LNet also maintains a database of all the peers it talks to. Each peer has multiple networks, and each network can have multiple interfaces. Next slide, please. To summarize, an LNet level multi-rail solution fulfills all the requirements we outlined. It reduces configuration complexity, allows us to use multiple homogeneous and heterogeneous interfaces simultaneously, thereby aggregating their throughput. It allows LNet to intelligently select local and remote interfaces based on its own selection criteria, as well as user-specified selection policies. Next slide. Let's walk through the different phases of the multi-rail project in brief, starting with the base multi-rail phase. Next slide. I already talked about why an LNet level multi-rail solution is the best solution, and it is mainly because LNet is the only layer which has all the bits and pieces required to make appropriate decisions on which interface to use. Next slide. One of the attributes which is key for LNet is RDMA throughput. Therefore, it is important to ensure that RDMA operations are done in the most efficient manner. On larger machines, it is common to have interfaces with specific NUMA affinity. It is therefore important when doing an RDMA operation to select the interface nearest the NUMA node the memory buffers to RDMA to or from is located. There are kernel APIs which gives us the NUMA affinity for both the interface and the memory. Therefore, LNet is able to select the best interface to send from. If there are multiple interfaces and all are equal from a NUMA perspective, then LNet keeps a credit count for each interface to keep tabs how busy each interface is, and it selects the most available one. If all this criteria is equal, then an interface is selected in round robin. What I just described is the algorithm is called the selection algorithm, and it is designed to be expandable and take into account other selection criteria such as the health of the interface being examined. It can also be expanded to handle other types of restrictions. For example, if the RDMA source or sink has affinity other than NUMA to the network interface, the LNet selection algorithm can be expanded to include this criteria in order to select the best interface to do the RDMA operation. Next slide, please. Let's discuss briefly how multi-rail can be configured thus far. The first bullet point shows how you can configure a network from both kernel module parameters and from a user space utility called LNet control. We're trying to emulate the IP utility model where it makes sense. This way, LNet configurations can be done from user space as opposed to having to specify module parameters. This is the only configuration step required. The discovery protocol is then used to discover the peers' interfaces on demands, as I mentioned earlier. As noted before, each node has a primary NID. A NID is composed of the IP address of the interface and network name. The primary NID is the NID of the first interface configured. So in this example, in the example on the slide, the primary NID is the NID associated with IB0. The concept of a primary NID is important because Lustre uses the primary NID to identify the node. Lustre remains agnostic to all the other interfaces available on the node. LNet manages these. When configuring LNet's virtual networks, interfaces of the same type must be placed on the same network, since the underlying wire protocol is not compatible. We don't want to get in the situation where LNet tries to send from an IB interface to an OmniPath interface, for example. It's also a good idea to place the interfaces configured on the same subnet on the same LNet network. Next slide. By the end of phase 1 of the multi-rail features, we were able to maximize the throughput. For example, tests have shown that if we run with two EDR IB interfaces, where each one has a maximum bandwidth of approximately 12.5 gigabytes per second, LNet is able to achieve approximately 23 gigabytes per second with 1 megabyte RDMA transfer block size. Next slide, please. Here's a more realistic Lustre performance test done in the early days of the multi-rail development. On that system, with a theoretical maximum performance of 34.6 gigabytes per second write speed and 86.4 gigabytes per second read speed, we were able to achieve 32 gigabytes and 68.6 gigabytes respectively. Next slide, please. So this is all well and good. However, what happens if an interface has an error or permanently fails? How will LNet react? After phase 1, LNet wasn't monitoring the interface's health, and if an interface fails, it will continue using it. Therefore, a percentage of Lustre traffic will fail. This is where phase 2, the health and resiliency, comes into play. Next slide, please. In this phase, each interface is assigned a maximum health value to start with. This is an arbitrary value which represents the healthiest state. In the case of LNet, we selected 1000 to be the maximum health value. LNet monitors each interface, and if the send fails on the interface, its health is decremented. The interface's lower health value will make it less favored in the selection algorithm, as the selection algorithm will always select the healthiest interface. In the grand scheme of things, that means if you have multiple local interfaces available for use, we always select the healthiest one. It's the same for the remote interfaces as well. LNet places the unhealthy interface on a recovery queue and pings it on regular intervals until it recovers to the maximum health value. It then can be selected again. To be clear, an interface will be selected even if it has a lower health value than the maximum, provided it has the best health value among the other interfaces. LNet will also monitor events from the OFID layer, such as IB event device fatal or IB event port error. If we see either of these, we immediately put the interface in a fatal state, and it will only exit the fatal state when we receive the corresponding up events. In this way, LNet does best effort at ensuring the healthiest path is selected. This logic is performed on every message sent, and this way the best path is always selected. Next slide, please. The other aspect of the LNet health feature is LNet level retries. This is pertinent when the local node has more than one interface or the peer has more than one interface. LNet will attempt to resend the message which failed over or to another interface. However, not all send failures will trigger a retry. If the message failed to egress the node, then we will retry. However, if it made it on the wire, LNet will not attempt to resend to avoid having to deal with duplicate messages. Portal RPC has an RPC level retry mechanism, which will kick in when LNet reports a failure. LNet retries are there to avoid heavier error recovery mechanisms when possible. Next slide, please. With both LNet Multi-Rail and Health under our belt, it was time to turn to the LNet routing infrastructure. First, we'll cover what exactly is LNet routing. Next slide. LNet routers are intended to connect two wire-incompatible LNet networks together. For example, an LNet TCP virtual network and an AutoIP virtual network cannot communicate directly. An LNet router is needed. Its basic job is to route LNet messages from the TCP network to the AutoIP network. A practical example is a case when you have the clients in one geographical location and the servers in a different geographical location. Clients will need to go over Ethernet to the servers, but then the messages need to be routed to the AutoIP network, which the servers are on, and the reverse is true. If a gateway has multiple interfaces on the same network, prior to multi-rail, each interface must have its own route configured on the nodes. Multi-rail routing redesigned the LNet routing feature to build upon the multi-rail infrastructure. Next slide, please. Unfortunately, this diagram is missing some lines. So imagine that the clients are connected to the gateways and the servers are connected to the gateways. Here's a simple example where clients are on the TCP network and servers are on the AutoIP network. The gateway in the middle routes between the two networks as I described. Next slide, please. Let's take a quick look at how to configure routes. The first bullet shows how a gateway is configured. I'll cover the first two parameters since these are the most important ones at this time. The --net parameter is the remote network we want to route to. If we're on a TCP network, then the remote network would be the AutoIP network and vice versa. The --gateway tells us the gateway NID to send messages to be routed. Since multiple gateways can be configured to the same remote network, the priority and hops serve as a way to select the route to use. If everything is equal, the routes are used in round robin. Next slide, please. The goal of the multi-rail routing feature is to deal with each gateway as a multi-rail capable node. We do not need to specify a different route to each gateway's interface. We only need to specify one route to the entire gateway. The multi-rail selection algorithm will make sure to use all the interfaces of the gateways as described before. This simplifies configuration and can reduce the number of gateways needed as the throughput through the gateways increased by adding more interfaces. Furthermore, there existed distinct code to keep track of the gateway's health. The code has become redundant as multi-rail health does the same job. Therefore, the code was redesigned to use the health capabilities to monitor the gateway's health. Next slide, please. Back to our example, again, it's missing some lines. Now the gateway has multiple Ethernet interfaces and multiple IB interfaces. No configuration on the clients or the servers need to change. The clients and the servers will discover the gateway's interfaces and make sure to use all of them. This feature made the routing infrastructure aligned with the way multi-rail works, and it added the multi-rail benefits already highlighted to routed setups as well. Next slide, please. The final phase of the multi-rail feature set is network selection policy. We're going through it right now, and we're trying to land it in Lustre 2.14. Next slide. The primary goal of this feature is to give the administrator fine-grained control over LNet traffic. Multi-rail added the ability to use multiple interfaces, both locally and remotely. However, realistically speaking, the underlying network topology might be designed such that some paths, although possible, are less efficient than other paths. There is no way for Lustre or LNet to figure out the network architecture it's running on. Therefore, it's important to allow the administrator to program policies which adds the intelligence within LNet. These policies will allow the administrator to assign priority to local and remote networks and even to specific NIDs. It will also allow them to assign a preferred list of remote interfaces to specific local interfaces. Let's take an example. If we have configured two networks, O2IB and TCP, the administrator might want to only use the O2IB as long as it is healthy and only use the TCP if there are no available O2IB interfaces. This can be achieved by increasing the priority of the O2IB network. Therefore, it will be selected above the TCP as long as it is healthy. Let's look at a more complex example. Next slide, please. In this diagram, you have two clients, each connected to a separate segment of the network. The red line between the two segments is a bottleneck. There's only one virtual network, O2IB in this case. Each of the servers have two interfaces on each of the network segments. Without any policies to guide LNet, it will send to both of the server interfaces. Roughly half of the traffic will go over the bottleneck and performance will suffer. Next slide, please. To avoid this, we can add a policy on client 1, which will help it avoid the red path completely. The policy here says that if you're going out of the 10.10.10.2 O2IB at O2IB NID, then make sure you only go to the servers which match the remote rule, or the server interfaces which match the remote rule. These are the 0.4, the 0.6, the 0.8, and the 0.10 NIDs. However, if one of these interfaces is not healthy, then select one of the other healthier interfaces. It is better to take a performance hit than to fail completely. Next slide, please. Adding, deleting, and showing these network selection policies can be done through the LNet control utility. Policies are serialized and sent to the LNet kernel module where they are applied on the existing constructs. The idea here is not to look up the rules on the fast path. Rather, we program the rules into LNet's data structures such that the selection algorithm can make decisions based on them without having to look up the policies. When a rule is added or deleted, it's done on the slow path, and the LNet data structures are updated accordingly. When new peers or interfaces are added on demand, the policies stored in the kernel are traversed and applied on the new data structure. Next slide, please. This covers the multi-rail feature set. Let's do a quick recap. Next slide. To summarize, multi-rail added the ability for LNet to increase the bandwidth by utilizing all existing interfaces simultaneously. This was done while reducing configuration complexity. With multiple interfaces available, LNet monitors the interface health and uses the best option available per LNet message. Network selection policies provide the administrators the ability to have fine-grained control over LNet traffic. They have the freedom to define these selection policies based on the underlying physical network topology. The multi-rail selection algorithm ensures the best interface is selected with emphasis on the best interface to complete the RDMA operations by examining the interface affinity compared with the RDMA source or sink affinity. Finally, since multi-rail features are implemented at the LNet level, other hardware added which require new network drivers will automatically benefit from the multi-rail features and will not have to re-implement any aspect of it. This covers the multi-rail feature set. Hope you found it useful. Next slide, and any questions, please.
Yes, I have a question here. What congestion control mechanisms is used in LNet Multi-Rail?
Right now, it uses the credits. So basically, every interface maintains the number of credits available for that credit. So for that interface, so we configure the number of credits, and then whenever we use it, we decrement the credits. And then when we're selecting the interface, we use the one with the most available credits.
Okay, thank you. Any other questions, please? Oh, what about end-to-end congestion control?
That is done by, there's no mechanism at the LNet level to do that. We rely on the underlying protocol for the end-to-end congestion control, whatever is provided via TCP, for example, or IB.
Okay. Any other questions? You can use the Q&A panel in your WebEx window to submit the questions. All right, then I guess that was the questions, Amir. Thank you very much for your time. And we recorded this presentation. We will be putting it online as soon as it is available to the host. The PDF presentations are also on our OFA website. I put the link in the chat window. So thank you, Amir, for your time.
Thank you.